to 11. So for this lab, we utilize Newton's second law and the energy principle to model the movement of a string. So these equations are like energy equals the kinetic energy plus the the potential energy due to gravity, and then the potential energy due to the spring. So this equation is K equals, it's 1/2 G velocity squared, and then the gravitational one is mass times gravity times height, and then the spring one is half times Ks, and then like L minus L naught squared. And then we use Newton's second law, which we've used a lot, which is Bf equals Vi plus F net over m delta T. And then we have final position equals initial position plus the average velocity times T. So this was my model in Tracker. And for this model, we were told that the mass is 0.402 kilograms, and the initial velocity was obviously 0 because it starts from rest. And then the initial position I got as 0.0116 in the x direction, and then negative 0.0116, and then negative 0.723, and then we're pretending like it's 2D, so z is 0. So, and then to compare to this, I made an experimental model using VPython, and then having my initial conditions based off my experimental model to match. So this was my position versus time in the top right, and my graph obviously looks a little wonky, but I think that's mostly due to like air resistance and the fact that like it's not a perfect scenario when you're doing it in person. So that would attest to like the slight changes and everything, and like air resistance and all that kind of stuff. And then we have our models and like all the energy. The potential energy and the kinetic energy and stuff. So the green is the potential energy due to the spring, and then the gravitational potential energy is the red line, and then blue is the kinetic energy, and then orange is delta E. So as we can see, like the energy principle and stuff like that is all satisfied because the orange line, which is delta E, so the change in energy is completely 0. And since this is like a closed system that we're modeling, that's your delta E is going to stay same, stay 0 the whole time because all these forces are perfectly canceling each other out. So this is my code itself. So we have the mass of the ball, so 0.402 kilograms, and then our initial position, which I got from my actual data, and it's starting from rest, so velocity is 0. We have gravity, and then we have the spring constant, which was calculated by 4 pi squared times the mass over t squared. And then we have L naught, which is L minus mass times gravity over Ks. So that's where I got this number from and from that number from. And then gravity is just 9.8. The next thing we have is the force due to gravity, which is just mass times gravity times a vector because it's only acting in the y direction. So it'd be like, and it's pulling down, so it's 0, negative 1, 0 for like that unit vector that you multiply by. We have the spring, which is negative Ks times S times L hat, which is just like the force acting on the mass by the string. And then net force is the gravity and the spring force, the like force due to gravity and then the force of the spring put together to give us F net. And then from that, we just plug that into the ones that we've been using this whole time, which is just Newton's second law. So Vf equals Vi plus F net over m times delta T, and then Rf equals Ri plus velocity times delta T. And then we have to like update our the location of the spring and like the equation, the numbers that we're going to plug into our the next equation, which is this one, so the equation for K, which is again, it's just half times the mass of the ball times velocity squared, and then we like calculate delta T and like all of these equations I've already said. So we have delta UG, which is the gravitational potential energy, delta US, which is spring potential energy, and then delta E total, which is E minus EI. So the final energy minus the initial energy. And from our graph, we can see that like these things have like always cancel each other out perfectly. So E equals EI because delta E is always equal to 0. And then this is just like to actually plot it. So like I've said, so the energy principle is satisfied, which we can see because like at any given point, all of these numbers will perfectly cancel each other out to be equal to 0, which is what we want because that means that like the energy within the system isn't changing. And then we have the period of oscillation. So we have like based off the X and based off the Y. So they're basically the same, which is like what we would expect. So thank you.